next speaker, we're very fortunate to have Danilo Rezende from Google DeepMind. So he's a senior staff research scientist and team lead there, and is well known for works connecting to invariance and physics. In fact, his website is named Invariance, so he's a perfect speaker for us. So Danilo, let's see if you can share your screen.
Yeah, thank you very much. Can you hear me well?
Yes.
Very good. So let me try to share my screen. Yeah, looks like it is good. Let me see. Can you see my slides?
Yes.
Very good. So I'll start. So I'll talk about some of the works we've been doing on incorporating symmetries, and in particular equivariance into generative models. Some of these ideas are very general and can be broadly applied in machine learning, but some are very specific to the problem we are interested. And I'll go through some of this in different degrees of generality. So please interrupt me if you have some specific question. This is the rough overview of the things I would like to talk about. And I will start with some general introduction, and I want to talk about some general principles first. First, how do you build something that's invariant to a given group, or how to build something that's equivariant to a given group? And then how do we translate that into normalizing flows, where we have extra constraints, where we're interested in building maps that are also diffeomorphisms. So what does it mean to how do you put these two constraints of equivariance and diffeomorphism together? And I'll show two papers, and I will go through two papers where we put these things into practice. So motivation, as a lot of people have already presented, including Taco just before me, there are many problems where we have known symmetries at the input, and either when we build some classifier, some density estimation, we know that the data has some symmetry in advance, and there are a huge number of such problems, and it's very easy to talk about physics, since physics is built on top of symmetry groups. But there are many other concrete practical applications that's not just fundamental physics applications. Just to give a general motivation of why I believe that we should always seek to incorporate into the architecture of our models rather than learn gauge invariance or symmetries into the models. So this picture is just to illustrate that if you're learning some density that has a direction where the action of a group along this direction or this manifold gives the density invariant, and you just build a joint density over all these degrees of freedom there. You may need, if you have a continuous group, in theory, you will need an infinite amount of data to learn the symmetry, whereas if the symmetry is built into the architecture of the density, so for any configuration of the parameters of your model, it will always correspond to an invariant density. It is like you have an infinite amount of data that comes from the future, because any test data point will also be evaluated against something that is already invariant. So this is I see as one of the main motivations for incorporating invariances and equivariance in machine learning. So more specifically, so Taco already explained some of these things very nicely, but just to give name to things, invariance and equivariance are very simple concepts. So if you have a map F, let's say a neural network that goes from space A to space B, and a group action. So here, most of the time, we'll be talking about a group action as a linear thing. So it's there's a matrix or a matrix representation of a group that acts on the input space of this function, we say that this function is invariant if the composition of the function with the group action is the function itself. And we say it's equivariant if we can commute the composition of the function and the group action. So these are very basic definitions. So this is what we mean when we talk about invariance and equivariance in the rest of the slides. So let me go through some general mechanisms that permeate pretty much every paper trying to build equivariance and invariance. So first, some of the things that Thakur also mentioned before are the idea of group convolutions. So group convolutions are completely general mechanisms. You can use them to build invariant maps. That's the easiest thing you can do. So if you have an arbitrary function phi, I can build an invariant function with respect to the action of a group on the inputs of this function by simply taking the average of this function over the group using the appropriate invariant group measure, invariant measure in the group. And similarly, you can build an equivariant map from an arbitrary map phi with a different kind of group convolution. Examples of that are convnets for the translation group, and for different kinds of groups, Taco's work goes in very nice details on how to build that in practice. So this is a very general mechanism. So what other mechanisms are out there? And so other types of mechanisms that might be useful if you're interested in directly building into the architecture the invariance and equivariance is to directly use group invariance. So for example, if you're interested in translational invariance, we know that distance between, so if the inputs of my maps are point clouds, I know the distance are translationally invariant to reach the translations. So I can build a map that it only depends on pairwise distance, for example. This would be by construction translational invariant map. And this has been explored in various GraphNets papers. For more complex, for different kinds of groups, so let's say some of the unitary groups like SUN, spatial unitary groups, and UN, etc. We are also interested in thinking about the matrix conjugation equivariance. This appears in many problems in physics, and a trivial group invariant to implement is the trace, and the traces of powers of the matrix. So if I want to build a function f that's in a neural net f phi that is invariant with respect to matrix conjugation shown here, the top equation, I can simply build a ordinary neural network f that is a function only of traces of powers of the input matrix. And this is extensively used in physics, in particular in lattice quantum chromodynamics, to simulate fundamental interactions. This is very well known in that field. Another general result that we can talk about is when you have orthogonal representations of a group G, we can build equivariant maps from invariant maps. So if you give me an invariant map with respect to orthogonal group, I can build a permutation. I can build a map equivariant to that group by simply taking the gradient. So that's what this little lemma that's used in a few different papers. And so, for example, the permutation group is an orthogonal group. I can use this little lemma to build a permutation equivariant map by simply first building a permutation invariant map, which is very easy to build, and then taking its gradient with respect to the input. And by construction, this will be a permutation equivariant map. So this is quite a general little result that we can use to build equivariance from invariance. Now, these are some general results that are applicable to any kind of maps. But when you're talking about flows, we're talking about diffeomorphism. So In normalizing flows, we are not dealing only with maps, but on maps that are both smooth and invertible. Now, how do we incorporate such constraints into flows? First, as I said, the purpose of normalizing flows is to build density by transforming a simple initial density into a complex density via diffeomorphisms that we compose through the layers of the flow, using a very simple formula for the change of density under diffeomorphism. We'll not go through details of specific details of how these things are trained, but there are various architectures of flows that have been published there. I'm not going through details now. That's not the point of the talk. We can view extend flows to non-Euclidean manifolds. There's various works doing that now. But the main result for incorporating one of the main results used to incorporate this equivariance and the symmetries into flows is this little lemma, which is the following. So if the initial density is invariant with respect to a group, let's say a Gaussian, for example, is invariant with respect to rotations with respect to the origin, so a spherical Gaussian. So if we start with an invariant density, and the flow is equivariant with respect to the same group, then the density defined by the flow is going to be an invariant density. So that's very intuitive and relatively easy to prove. It's very easy to prove, but this is a main result used to build the invariant densities with flow. That means that from an equivariant flow, I can build an invariant density. Another general result for flows, which is very important for physics applications, is about matrix conjugation equivariance. So if I want to build a diffeomorphism on unitary matrices that is equivalent with respect to matrix conjugation, then we can prove that this is equivalent to building a via equivariant flow in the maximal torus of the group. So let's expand what that means. So for special unitary groups and unitary groups, the maximal torus of the group is simply a space of the eigenvalues. And the eigenvalues, they live in a torus for these groups. The eigenvalues of the elements of the group, they live in a torus. And what this proposition says is that if I want to build a matrix conjugation equivariant diffeomorphism on SUN and UN, and that result also extends to a special orthogonal group, for example, and orthogonal groups, it is sufficient to build a via equivariant flow on the maximal torus, which in turn is just a space of eigenvalues. And it turns out that for these groups, the via group is a very simple thing. It is just a permutation group. So we established this equivalence between matrix conjugation equivariance and permutation equivariance of eigenvalues. And this points to a link that leads us to this observation that the permutation group is key to build many kinds of equivariances. So even when I talk about continuous symmetries, the permutation group is going to appear somewhere. And if you have very good tools to build invariant flows and maps with respect to permutation groups, this can be very broadly applied to many problems. So that's a very interesting observation, I think. So just to expand a little bit this idea, what I mean, how to build a permutation equivariant or via equivariant flow on SUN. So as I said, the maximal torus of SUN is the space of eigenvalues. So if I do an eigen decomposition of SUN element, it can be written like this. And I can visualize, here I'm just visualizing the what we would call the uniform measure on this group. So this is the Har measure, which is the unique left invariant measure on the group. And if you plot as a function of the angles of the eigenvalues, it looks like that. As you can see, it has this six-fold symmetry, which is each of this cell is a perfect copy of the other cells. So a general mechanism to build a equivariant flow there is to have a canonicalization map, which maps a point on every cell to a canonical cell. Then we can build a flow on that cell and apply the inverse of the canonicalization map. So that's a very general algorithm that in some cases can be implemented very, very efficiently. So this has been explored in a few papers. Two of the references are here. And here I'm illustrating, so in this figure, I'm illustrating how these cells look like for SU2, SU3, and SU4. They are n simplexes. And so for the special unitary group, we can show that these cells, they are n simplexes. So you can reduce the problem of building a conjugation equivariant flow to the problem of merely building a flow on a simplex, which you can do following a very simple idea where we map a simplex to a box, apply a standard flow there, and then go back to the simplex. So that's a very simple idea, but that allowed us to build a very, very broad range of equivariant flows with respect to value group and matrix conjugation groups for special unitary groups. And then as a consequence, it allowed us to build gauge SU3 gauge equivariant flows to do QCD experiments. So that's what's one of the first applications I want to mention. I will not enter into the details of the physics of the problem, but this flow, it really combines pretty much all these ideas that I have discussed up to now into a single piece of code. There we demonstrate that in order to build a gauge equivariant flow, we can reduce this problem to build a matrix conjugation equivariant flow, and then apply all these little lemmas that reduce the problem to building a simplex flow on the invariant cell of the SUN group. And this allowed us to build arbitrary densities for SUN for theories on SUN, not just for n equals 3, which corresponds to QCD, but for arbitrary n. So, for example, here on the left, we show examples of densities that appear in QCD on the maximal torus of a single SU3 element. So, as we've seen before, these densities, they are two-dimensional densities, and they have the six-fold symmetry because there are 6 cells for SU3. But when you go from the group SU3 to the group SU9, now SU9 has more than 300,000 such cells, and it's very hard to imagine how we would be able to build a flow there. But with this completely general result, we can still build it. And here on the right plot, we show obviously two-dimensional slices of this 8-dimensional density that has 360,000 something invariant cells. So we can apply this to also generalize the results for UN and a few other groups. Another work that we've been doing before this is thinking the Hamiltonian formulation of mechanics and building Hamiltonian flows. So the main motivation to think about Hamiltonians in the Hamiltonian flows is that the Hamiltonian formulation of mechanics comes with a very nice language to deal with symmetries. So in the Hamiltonian formulation of mechanics, symmetries are simply functions that commute with the Hamiltonian. And I'll expand a little bit more what commute means in this context. These are just some general definitions there, but you don't have to go into too many details. So the Hamiltonian dynamics is defined on a state space of position and momentum variables. Position lives, let's say, in R n, and the momentum variables, they actually live in the dual of the tangent of this space. So they are linear operators acting on the tangent space of the manifold. But the dynamics of in this state space is described by what's called a Poisson bracket, which is this operator that applies that we apply to any variables or functions of the state space variables to the Hamiltonian. And it is generally defined as this formula at the bottom in a Euclidean space. So this gives basically is a way of constructing a ODE. Now this ODE has very special properties. So this is just a recap of what is called a canonical and infinitesimal canonical transformation with generator F. So the Hamiltonian dynamics is an ODE where the temporal evolution is given by a sequence of infinitesimal canonical transformations induced by the Hamiltonian function. And this dynamics, it has a constant divergence, so the divergence is zero, is a constant value. So that means that it's a volume-preserving flow. So Hamiltonian dynamics is volume-preserving. And it's also invertible. And when we discretize time, these things may not be exact anymore, but they will be, obviously, there will be discretization efforts to be dealt with. So we can build a normalizing flow as we build any flow, any ODE flow by a composition of infinitesimal transformations. And on practice, it looks like this. You can start with an initial density, let's say a Gaussian on the state space, and you obtain an arbitrary density on the output space. This is just to show that it works on some toy examples. But what's interesting here is that now we can use all the very nice formulation of symmetries in the Hamiltonian formulation to talk about symmetries in normalizing flows. So a symmetry generator, what we call a symmetry generator in the Hamiltonian dynamics, is simply a function that commutes with the Hamiltonian. So any function such that the Poisson bracket that I defined before with the Hamiltonian is zero will be a symmetry generator. And very similar to this little lemma that we talked before about how to build invariant density using equivariant flows, we can use a discrete version of Noether's theorem here to talk about how a Hamiltonian flow is going to define an invariant density. Here we have all these error terms because the symmetries of the Hamiltonian dynamics are only exact in continuous time. So when we discretize, we introduce errors which break the symmetries. And you have to account for these errors in practice. So what we did in this little application was a very exploratory work. Instead of building the invariances directly into the Hamiltonian function defining the flow, we imposed that then via Lagrange multipliers. So now we are imposing the constraints via optimization rather than on the architecture. I do not believe that this is the ideal way of doing this anymore, simply because you may lose all the advantage of the data efficiency of the problem by doing this. However, in some problems, it is not obvious how to incorporate the symmetries into the architecture, and this might be the only viable alternative there. So we apply this to a very simple problem where the symmetry is just the symmetry of a SO2 group that has a very simple generator, which is bilinear, skew-symmetric bilinear function. And what we demonstrated there is that if the target density has such a symmetry, but you have only a finite amount of data points, a flow that is unaware of the symmetry will very quickly overfit to the training data. And when we evaluated the test set, it will have very low likelihood. Basically, it should converge to a mixture of deltas at the training points. However, a flow that knows about the symmetry should never converge to a mixture of deltas. It should naturally accommodate this circular shape of the density, and this should extend to the any test data. And that's what to observe in this little experiment here. So thank you for your attention. I'll be happy to discuss and yeah, chat about these problems now.
So thank you very much for the nice overview of all these different works. And so if there are any questions from the audience, please use the Q&A. So yeah, so that one question over there. There are some questions about this Lagrangian multiplier and
yes.
Like constrained versus yeah, regularized. How does it affect the equivariance?
Exactly. So the Nether theorem doesn't care how the symmetry is imposed on the Hamiltonian. But when imposed via Lagrange multipliers, obviously the symmetry is not going to be imposed exactly, unless the Lagrangian Lagrange multiplier part of the optimization really converges to the globe optima. Then the symmetry is going to be only an approximate symmetry. So in this case, we are talking about we have to think about a approximate version of another theorem, which is what you have to think anyway when you're talking about discretized equations. So another theorem, more broadly speaking, it simply says that if there's symmetry in the Hamiltonian, there will be some functions which are constant over time. And in practice, what is going to happen is that there will be functions that are almost constant. And these will be the approximate generators of the symmetry. So this is the change you have to do. You have to deal with an approximate another theorem when the symmetries are not exact in the Hamiltonian.
So I guess more maybe basic question is somebody was asking about what is could you explain a little bit more about what a flow is? Partly maybe you can explain a little bit, but I think there's a lot of references on this out there, and so maybe it is a little yeah, maybe it's too basic, but maybe you can explain.
Yeah, so flow, yeah, not just the Hamiltonian, but yeah, there's a question about more linked to more references about equivalent Hamiltonian flows. Yeah, I can point to some. So there's a so if you go to the slide to my webpage, I have lots of slides there that talk about Hamiltonians and things like that, so that you can search more references about Hamiltonian flow there. But now flows specifically, I'm sorry if that was not clear. I should have really, they should really have been more clear. So a flow is simply any diffeomorphism that apply to a density. And more specifically, what we refer to a normalizing flow in this context is the path taken by the initial density to a final density via a sequence of diffeomorphisms, via a sequence of composition of diffeomorphisms. So we call this normalizing flow, borrowing the name from fluidodynamics, where you refer to a flow of a fluid that conserves mass, and here what's being conserved is probability. So when you talk about flows, we're just talking about a sequence of composition of a sequence of diffeomorphisms that you can cheaply implement with the neural networks.
Great. Thank you very much for explaining that, and thank you for the nice talk.